Hey guys, I thought I'd make this video for 10.2 because there was a handful of students that missed this Friday. And unlike what I said the time before, I don't think we need 2 days on this, so we're only gonna take one day. So the next time on Wednesday, that would be Wednesday the 22nd. That's gonna be 10.3. But 10.2 honestly isn't too bad. So what I would like you guys to do first of all is that I posted a YouTube video on 10.2. So if you go into modules and 10.2, you'll see my notes and you'll see this video. And what I'd like you to do is watch the first 13 and a half minutes or so of this video and then come back to this video where I'm just going to go a little bit more in detail about what they're talking about to formalize a definition of a Taylor series. So go ahead, give that a watch. I think it's very good. It's very visual, which is one of the best things you can have for series because a lot of times talking about series can be very abstract and not so visual. So go ahead and watch that and come on back. So if you have watched it and you're here now, um, what the video essentially talks about is taking a function, any type of a function, um, and finding a polynomial to represent it. So in 10.1 we had a series, so we were given a series, say x to the n power. And this right here, if you built out the series, you'd be given 1 plus x squared plus x to the third, so on and so forth. And what we were able to do is to see that this series is a polynomial function, and this polynomial function converges to a different function, and I think we said that this was equal to f of x is equal to 1 over 1 minus x. So given a series, can we find a polynomial function to represent a non-polynomial function? Now, essentially in 10.2, what a Taylor series is when you take a function and can I find a polynomial or a polynomial series, a power series to represent it? So it's like going in the other way. And in that video, what they did is they took cosine of x around x equals 0, right? And so what that might look like around x equals 0, so say that you have your graph right here. So here is the function of cosine of x, and what they said is that they found a quadratic that really closely resembles the function around x equals 0, and they told you how you can get that function. But essentially what it comes down to is that a polynomial looking like a sub 1, or let's say a sub 0, so say you have a polynomial a sub 0 plus a sub 1 times x plus a sub 2 times x squared plus a sub 3 times x to the third plus so on and so forth. Essentially, that in order to get a polynomial to match a non-polynomial function at a certain point, it really just depends on the derivative of this function. So for cosine of x, well, if I wanted a quadratic to resemble cosine of x, first of all, their outputs needed to be the same at where it's centered at. So this case right here, that's 1. And then they said, well, we need the slopes to be the same. So they knew cosine, the derivative of cosine, which is sine of x, and sine of x at 0 is 0. So that's why this was 0 right here. So essentially, the first derivative of cosine, so d dx of cosine, had to be equal to the first derivative of the quadratic, we'll just say of f of x. These had to match. And so that's what they did. They took the derivative of this right here, took the derivative of cosine, and then they set them equal to each other, and they were able to solve for this constant right here. And then they said, well, we need the second derivative to match, and then if you want to go any further, you just have to keep matching them. So what it came down to is that these constants in this polynomial can be found, so on and so forth. So a sub n times x to the n. This variable, right, this constant right here is really what we need to find. And if we can find a way to calculate any constant of any term, really just depends on the function that we're trying to model it. We just have to match the derivatives. And so that's what a Taylor series is. So I'll show you the general proof of how you can do that. So let's say that we built out a series. So this series, so we'll say we have a series starting at 0, and this is a sub n times by x minus c to the n power. So this is a power series, right? And then this power series, when you build it out, you get something like a sub 0. Now a sub 0 is just going to be the constant in front of that constant, and then plus a sub 1 times by x minus c to the first power, plus a sub 2 times by x minus c squared, plus a sub 3 times by x minus c cubed, plus all the way until you get to a sub n times by x minus c to the nth power, and even more terms after that. So here's the power series that it produces, produces right here. So our objective really is to find a way to find whatever this constant is right here. So because this doesn't matter too much, x minus c to the n, this is determined by the where it's centered at and the degree of the term. This is what's going to differ right here for any sort of function. So if I were to have sine of x, natural log of x, square root of x, say I were to find a polynomial to represent it, these polynomials are all going to have an a sub 0 term. Okay, they're all going to have an a sub 0. They're all going to have a sub 0. They're all going to have an a sub 1x, a sub 1x, a sub 1x. They're all going to have an a sub 2x squared, a sub 2x squared, a sub 2x squared. So note that these are always going to be the same. It's just that these constants are what's going to be different. And so that's what we need to find. So this right here is what I'm trying to find. So let's say that this is a function. So this part over here is the sine of x, natural log of x, square root of x. And then over here on the right side is the polynomial. Okay, well, like you saw in the video, it really just depends on these first derivatives. So if a sub 0, which is the constant term, has to be equal to whatever this is centered at. So essentially right here, so say we're centered at 0, at x equals 0, then well, we'll get to that in just a second. So here is our function f of x. So so let's say that, well, instead of being centered at 0, let's say we center this polynomial at c right here. So then that means f of c, note that all of these are just going to go away. And so if I want them to match, I do f of c, and you can see that the only thing that remains is this first term right here. Okay, so then a sub 0 is going to be equal to whatever f of c is. Okay, now let's say I want to find a sub 1. Well, I want their first derivatives to match. A sub 1 means that the first derivatives need to match. So f prime of x will be equal to, the derivative of a sub 0 is 0. The derivative of this right here would be a sub 1. And the derivative of the next term would be 2 times a sub 2, because I'm going to drop that downward. So 2 times a sub 2, and then I'll have x minus c, and then I'll have 3 times by a sub 3 times by x minus c squared, plus, and then for the nth term, whatever that might be, I'll drop down the n. I'll have times by a sub n, I'll have x minus c, then I'll have n minus 1. Okay, now again, if I want to find what a sub 1 is, note that if I just take the derivative at c, note that these are going to go to 0, and so the whole thing is going to go to 0. So I'll just write this out. So f prime of c is going to be equal to a sub 1 plus, all those are going to be 0, so it doesn't matter. So a sub 1 will be equal to the first derivative of that function at c. Okay, we'll say I want to find a sub 2 then. If I want to find a sub 2, I'm going to need to use the second derivative. So f double prime of x will be equal to 2 times by a2. That's going to be 0, and that's the derivative of that term right there. The derivative of this term, I'm going to drop the 2, so 3 times 2. Derivative of this one, I'm going to drop the n minus 1, and that's going to become n minus 2. So then I'm going to have plus 3 times 2 times a sub 3 times by x minus c to the first power plus all the way to n times by n minus 1 times by a sub n x minus c to the n minus 2. Okay, so then if I want to find a sub 2, I'm going to take the derivative specifically at c so that all of these terms go away. And so then I'll have f double prime of c is equal to 2 times by a sub 2. And a sub 2 is going to be f double prime of c divided by 2. So then that's how I can find the constant for a sub 2. Alright, we're just going to keep going until this gets a little too much, but let's say I want to find a sub 3. So if I find the third derivative, note that I'm going to drop the 1 down here. This is going to go to 0, and then I'm not going to have my variable here. So 3 times 2 times 1 times a sub 3 plus all the way till, now I'm going to drop the n minus 2, and that's going to become n minus 3. So n times by n minus 1 times by n minus 2 times by a sub n times by x minus c to the n minus 3. Keep going after that. So if I want to find a sub 3, we'll take the derivative specifically at the center. So it's c minus c. That goes to 0 all the way through. So then the third prime of c will be equal to, we'll just call this 3 factorial times a sub 3. So a sub 3 is equal to the third derivative at c divided by 3 factorial. Okay, now you can kind of see a little bit about the pattern and how factorials play a role. So just one last time, let's do the nth derivative. So we're going to stop doing the third, fourth. We're going to jump straight to the 50th or the 100th or the 1000th derivative, whatever derivative I need, in order to find a sub n, which is what I want. I want to find the nth term derivative. So note that if I take the nth derivative up until this, everything before this term is going to be 0 because they're going to be constants, and the derivative of constants is 0. Okay, so if I take the nth derivative, well, n amount of times, note that I'm going to keep dropping down this power. So I'll have equal to n times by n minus 1 times by n minus 2. And if I take it n amount of times, I'm going to get 3 times 2 times 1 times by a sub n x minus c. And if I take the derivative n amount of times, I'll have n minus n, which will be 0. So this is just going to go away right here, which is what happened on all of these other steps right here. We didn't have a variable term. Okay, and then plus everything after this. Now, everything after this will have an x minus c, so you'll have x minus c to the n plus 1, and so on and so forth. But it won't matter, because I'm trying to find the a sub n term, or the a sub n coefficient right here. So then if I take the derivative specifically, so at fn of c right here, note that this, all of this right here is just n factorial. So this is going to be n factorial times by a sub n, and then if I take it at c, that's going to become, this is already gone right here. This right here is equal to 1, so I don't need to worry about that. And then all of these terms are going to go to 0, so I have this right here. So finally, a sub n is going to be equal to the nth derivative at where I'm centered at, divided by n factorial. And this is literally the same thing that we use to find a sub 0, a sub 1, a sub 2, a sub 3, and so on and so forth. It's just the pattern that we use to find whatever coefficient I need for whichever term that I need. So therefore, I have this right here, which can replace this in my power series. So this is by the way, this is the definition of a Taylor series. So a Taylor series, so we have the series at n equals 0. Now instead of saying a sub n, which is the coefficient, we know how to find the coefficient. It's the nth derivative at c divided by n factorial times by x minus c to the nth power. And there you have a definition of a Taylor series. And now a Maclaurin series is a Taylor series, just c, or where you're centered at, is equal to 0. So the nth derivative at 0 divided by n factorial times by x to the n. This is a Maclaurin series. Okay, so let me go through a couple examples to kind of be a little bit more concrete in what a Taylor series does. So here we want to construct a polynomial like this that matches the behavior of the natural log of 1 plus x at x equals 0 through its first four derivatives. Now, first four derivatives, we call this a fourth order Taylor polynomial. Now notice that there is a difference between a Taylor polynomial and a Taylor series. Taylor series will use sigma notation and will look like this. A Taylor polynomial is when you truncate the infinite series at a certain term, so in this case at 4 derivatives. So here's how I like to set up these problems. Essentially, all I really need to do is find a sub 0, a sub 1, a sub 2, a sub 3, and a sub 4. I'm just looking to find what those coefficients are. So I'm going to use this pattern right here. I'm going to use f of x and its derivative. So in this case, f of x is defined as the natural log, so f of x is equal to the natural log of 1 plus x. So what I like to do is just start by taking as many derivatives as you need of this function. So that's what I did here, took as many derivatives as I need to find all of my coefficients. So I want up to 4 derivatives. So the first derivative of this right here would be 1 over 1 plus x. The second derivative, so I'm going to give myself a little bit more space. So the second derivative of x is going to be equal to, well, note that this is the same thing as 1 plus x to the negative 1. So this would be negative 1 over 1 plus x squared, like that. Okay, now the third derivative at x is going to be equal to, so this is negative 1 plus x to the negative 2. So I'm going to make it 2, and then it's going to be 1 plus x to the third. And then finally, the fourth derivative at x is going to be equal to, so this is 2, 1 plus x to the negative 3. So negative 6 over 1 plus x to the fourth. Okay, so I have all the derivatives that I need. Okay, now I'm going to use this right here, which is the nth term. So if I want to find, or sorry, the nth coefficient. So if I want to find a sub 0, then I'm going to use the 0th derivative at 0 divided by 0 factorial. Just a note, I know it's confusing. N factorial is, 0 factorial is equal to 1, and so is 1 factorial. That's equal to 1. If you need an explanation, I'm sure there's plenty of YouTube videos that you can find to show you why 0 factorial is 1. But in any case, so a sub 0 is going to be equal to the 0th derivative at c. In this case, c is 0 divided by 0 factorial. So if I plug 0 in here, that's why I like to line these up with over here. So I'm going to plug 0 in here. So the natural log of 1 plus 0 is the natural log of 1, and natural log of 1 is 0. So this is going to be equal to 0. There you go. So we just found out this term right, or that coefficient right there. Okay, now a sub 1 will be equal to the first derivative at 0 divided by 1 factorial. So that's going to be equal to, plug 0 in here, so that's going to be 1, and 1 divided by 1 factorial is equal to 1. Okay, the second coefficient is this, so this is going to be the second derivative at 0 divided by 2 factorial. So if I plug 0 in here, that's 1 squared. This is going to be negative 1, so negative 1 divided by 2 factorial is equal to negative 1/2. The third coefficient is going to be equal to, so I'm going to do the third derivative at 0 divided by 3 factorial. And so if I plug 0 in here, that's going to be 2. And then 2 divided by 3 factorial is equal to 2 over 6, which is equal to 1/3. And then the fourth derivative, so the fourth coefficient is the fourth derivative at 0 divided by 4 factorial. And if I plug in 0 here, I'm just going to have negative 6. So this is going to be negative 6 over 4 factorial, which is 24. So that's equal to negative 1/4. So finally, so my Taylor polynomial, which is of the fourth derivative or fourth degree, whatever you however you want to put it, that's usually the notation you would use, would be equal to, well, so we figure out the first coefficient is 0. The second coefficient was 1, so 1x. And then the second coefficient right here, so minus 1/2. Now this is going to be x squared plus the third coefficient, x cubed, minus the fourth coefficient, x to the fourth. And this polynomial will behave very, very similar to the natural log of 1 plus x at x is equal to 0. So if you want to graph these together, so natural log of 1 plus x and this function right here, you'll see that at x equals 0, they're pretty dang close to being the same. So here's the polynomial and here's the function. So pretty cool. Okay, we could probably just do do I want to do this one? You guys could probably, no, I'll help you out with this one. Okay, so it says construct a 7th order Taylor polynomial and the Taylor series for sine of x at x equals 0. So 7th order, meaning I'm going to take the derivative 7 times. So my f of x that I'm using is sine of x. Now if I take 7 derivatives, so f prime of x, f double prime of x, triple prime of x, fourth derivative, fifth derivative, sixth derivative, and seventh derivative at x. So the reason why we're going to take so many derivatives is going to be more apparent as we start building it out. So, but the first derivative is cosine. The second derivative is negative sine, then negative cosine, then sine. Then we're going to repeat. It's going to be cosine, negative sine, and then cosine. Negative cosine, that is. Okay. Alright, so to find a sub 0, this is going to be equal to the 0th derivative, in this case at 0, because that's where we're centered at, divided by 0 factorial. So I'm going to plug 0 in here. Sine of 0 is 0. This is just going to be 0. Okay, cosine, so for the first coefficient, this is the first derivative at 0 divided by 1 factorial. So cosine of 0 is 1, so this is just going to be equal to 1. The second coefficient is going to be the second derivative at 0 divided by 2 factorial. This is just going to be 0, because if I plug 0 in here, I'll get 0 on the numerator. And then a sub 3 is going to be equal to the third derivative at 0 divided by 3 factorial. If I plug in 0 here, I'm going to get negative 1 over 3 factorial. So I'll just write negative 1 over 3 factorial. I'm not going to actually do 3 factorial, and I'll show you why as I build this out. Now a sub 4, this is just going to be 0, because if I plug in 0 to sine, I'm going to get 0. That's going to be the same thing for this one over here. So the sixth coefficient is also going to be equal to 0. And now the fifth coefficient is going to be equal to the fifth derivative at x divided by 5 factorial, which is going to be equal to 1 over 5 factorial. And you should notice a pattern. A sub 7 is going to be equal to negative 1 over 7 factorial. Okay, so now I'm going to make another list. So I'm going to note that everything that's 0 or even is just going to be 0. So for example, this would be 0x squared, which is just going to be 0. So there's no x squared term. There's no x fourth term. There's no x to the sixth term. So those are all gone. So essentially, my coefficients are 1 and a sub 3, which is negative 1 over 3 factorial, a sub 5, which is 1 over 5 factorial, and a sub 7, which is negative 1 over 7 factorial. So now it also says in the problem, it wants you to construct a Taylor polynomial as well as a Taylor series. So for the Taylor series is what I'm going to do first right here. So I want to find a rule for my nth coefficient. So I'm going to build it off of the coefficients that I have here. So notice that my coefficients, my denominators and my coefficients are just prime, or not prime, they're all odd. So 1 factorial, 3 factorial, 5 factorial, 7 factorial. Okay, that also means right here, for my first term, this is just going to be 1, but for my third term, it's negative 1 over 3 factorial, and it's going to be x to the third. This is going to, my fifth term is going to be 1 over 5 factorial, and x to the fifth. My seventh term will be negative 1 over 7 factorial, x to the seventh. So this is what my polynomial would look like. Now I'm trying to build my series. So in order to do that, I have to notice some patterns happening here. The first pattern that I notice is that it's positive, negative, positive, negative. If that is the case, this is an alternating series. And the best way to write an alternating series is to write negative 1 to the n power. Because depending on n being odd or even, it's going to change to positive, negative, positive, negative, positive to negative. So that's how we get this right here. Okay, alright, so you can see that we're changing positive, negative to negative to positive. That's how we're going to get this right here. Now, as for the actual coefficient, so 1 over 3 factorial, 1 over 5 factorial, now the numerator is always going to be 1, or I can pretty much leave this on the numerator, but my denominator is always odd. In order to write an odd pattern into a series, you use either 2n plus 1 or 2n minus 1, depending on which term you're going to start with. So in this case, I'm going to write it as 2n plus 1. Okay? So this right here is 2n plus 1 factorial. Factorial. So notice that if n is equal to 0, then this will be 1 right here. And then this is going to be negative 1 to the 0, which is going to be 1, so that gives me my first one right here. Okay, so then let's say n is equal to 2, so then, or n is equal to 1, so then I'm going to have 2 plus 1, which is 3 factorial. Well, that's what I have here. And then if n is equal to 1 here, that's going to be negative, so it's negative here. If n is equal to 3, then I'm going to have, n is equal to 2, that's going to be 4 plus 1, which is 5 factorial. And then you can see that if n is equal to 2, that's going to make it positive. So you can see the pattern play out in this rule that I just wrote. Now as for this part right here, my x's, that's what I need. This is going to be x to the, now I'm going to write a rule for this, but the rule, as you can see, follows the same pattern as the denominator. 3 factorial, 3, 5 factorial, 5, 7 factorial, and I don't know why I wrote a 6, that should be a 7. But you can see that it follows the same pattern. So 2n plus 1 will give me odd powers. Okay. I guess I should write that in the next step. So my Taylor polynomial, or my Taylor series, is starting at n equals 0, is negative 1 to the n over 2n plus 1 factorial x to the n plus 1, or 2n plus 1. And there you go. We have our Taylor polynomial, or Taylor series. And my Taylor polynomial, I'll just say it's right here. That's my Taylor polynomial. Okay. We can try another one. So let's try this one right here. Notice that this one is not going to be centered at 0. So find the Taylor series generated by f of x equals e to the x at x equals 2. So notice that it just says the Taylor series, not the Taylor polynomial. So it wants the rule pretty much. This is the rule with sigma notation. So that's what we're looking for. So I'm more interested in the pattern that's being created than actually simplifying anything that's going on. So, but for the process, I know my f of x is equal to e to the x. And note that no matter how many derivatives I take, fn of x is always going to be equal to e to the x. So if I want to find the coefficients of my polynomial, well, a sub 0 is going to be equal to, a sub 0 is going to be equal to the 0th derivative, but in this case it's at 2 divided by 0 factorial. So if I plug 2 in here, I get e squared divided by 1, so it's just going to be e squared. Let's say I want to take, well, it doesn't really matter how many, notice that for like the third or something, this will be the third derivative at 2 divided by 3 factorial. Well, again, if I plug 2 into this right here, I'm just going to have e squared. So this is going to be e squared divided by 3 factorial. So that pattern is going to remain the same all the way to the nth coefficient. So my nth coefficient is going to be e squared divided by n factorial. So again, I'm more interested in the rule right here. So here's a rule for my coefficient. Now, as for the polynomial, so this would, my polynomial would look like this. This would be e squared plus, the next one would be e squared x minus 2, that is. So x minus 2, that's something that's different if it's not centered at 0. So x minus 2, then it's going to be plus e squared divided by 3 factorial times by x minus 3 squared. Sorry, that should be 2 factorial. Okay, and then so on and so forth. So my pattern, my nth term would be e squared divided by n factorial times by x minus 2. Sorry, that should be x minus 2 to the nth power. So that's my nth term. So to write my series, I'll just use my nth term as my rule. N factorial will have x minus 2 to the n power. And there's my Taylor series. Okay, trying to finish this up just so it's a quick video. For example 5, it says find the third order Taylor polynomial for this polynomial function right here at x equals 0. So note that this polynomial is a Taylor polynomial at x equals 0. So x, x, x. So if you were to do the whole process, which you could, you can write out this whole process. You can find the first 3 derivatives. You can try and find the coefficients, but you'll just get the same exact polynomial. It is a polynomial. So trying to find a third order Taylor polynomial of a polynomial specifically at x equals 0, you're just going to get the same thing. Now, for x equals 1, that's going to be a little bit different because this is obviously not one that's centered at 1. You can see it, if it were, it'd be x minus 1, x minus 1, x minus 1 right there. So that will change. So you can go ahead and do the same process, but use x equals 1. It will look a little bit different. The coefficients won't be the same, and this will be x minus 1. But yeah, so just note that if it's asking you to find a Taylor polynomial of a polynomial, note that where it's centered at, because if it's asking you to find it at x equals 0, well, that is exactly what you'll get from doing that process. So okay, and last but not least is this one right here. So example 6, building series from known series. So there's a table that you'll need to use in chapter 10. So it's right here. So it's this table right here. It's on these 2 pages, so page 499 and 500, but these have common Maclaurin series already built out. So e to the x, 1 over 1 plus x, 1 over 1 minus x. So we already found that Taylor series. We found this Taylor series today. And then here are some other ones. I think, yeah, we also found this one right here. Maybe we didn't. Maybe it was 1 minus x. I think it was 1 minus, or x minus 1. But in any case, we can actually use the concepts of functions and series to find functions, like a composition of functions and transformations of functions. So I'm going to take a small snippet of this, e to the x, because this is the one that we're going to use. Okay, also just a really quick note that sine of x and cosine of x and e to the x, so when I say e to the x is equal to this infinite polynomial and sine of x equal to this, notice that for 1 over 1 plus x, when we found this polynomial, we found the polynomial that converged to this function, we had to state that it was only between 1 and negative 1. So these were equivalent. This was called the interval of convergence. Something that's really interesting about sine of x, cosine of x, and e to the x is that these are three special functions where you actually converge to, it will converge for all x. So the more terms I add on to this Taylor polynomial, it's actually going to keep converging for the whole domain from negative infinity to positive infinity, same as sine of x and cosine of x. So just really wanted to quickly mention that. Okay, so here I have e to the, this is a Taylor or Maclaurin series, that is, and I want to find a function, so I want to find a polynomial that will represent e to the 2x minus 1 over 3. So first I'm going to focus on this part right here. So let's say f of x is equal to e to the x. Let's say I wanted to write a new function, g of x, which is equal to e to the 2x. Note that I can still use the composition property here. So all that's different is e to the x and e to the 2x. So I can go ahead and just use a composition of 2x for all x's. So this would be equal to 1 plus, well, instead of x, it's going to be 2x plus 2x squared divided by 2 factorial plus, and the next one would be 2x cubed divided by 3 factorial plus all the way till 2x to the n divided by n factorial. So the series right here would be this series of 2x to the n divided by n factorial for all real x values. Okay, well, let's take it a step further. What is 2x minus 1? So let's, I don't know, just a new function, e to the 2x minus 1. So if I subtract 1 from e to the 2x, and this is e to the 2x, note if I subtract 1, I would just get rid of this 1 that's right here. So e to the 2x minus 1 is 2x plus 2x squared divided by 2 factorial plus 2x to the third divided by 3 factorial plus we'd have 2x to the n divided by n factorial. And then last but not least, we'd have 3 divided by 3. So if I wanted to have another function, I'll just say I to the x. This would be equal to, so e to the 2x minus 1 divided by 3. So let's build off of what I had before. I'm just dividing this whole thing by 3. So every term can be divided by 3. So 2x divided by 3 plus 2x squared divided by 3 times 2 factorial plus 2x to the third divided by 3 times 3 factorial plus all the way till 2x to the n divided by 3 times n factorial. Okay, and there you go. We just built out that. Now, because the interval for e to the x is all real x, and we use that Maclaurin series all the way through, well, we can also state that this polynomial will represent this function for all real x values. Okay, so, but yeah, hopefully that wasn't too bad. Let me know if you have any questions next time you see me, but I hope this helps.